Okay, for this video we're going to talk about nuclear radiation and decay, specifically alpha, beta, and gamma particles. And here's a table that shows the alpha, beta, and gamma particles and the Big Mac symbol. You see that we have an alpha particle is helium, nucleus, it's got a mass number of 4 and an atomic number of 2, along with beta and gamma, neutron and positron particles. And there's a video here that I want you to see that's going to explain this.
Ernest Rutherford confirmed that radioactivity involves 3 different types of radiation: alpha, beta, and gamma. Alpha radiation consists of positively charged helium nuclei, that is, 2 protons and 2 neutrons. The radioisotope americium-241, used in smoke detectors, emits alpha particles. The parent nucleus contains 95 protons and 146 neutrons, making a total of 241 nucleons. When an americium atom decays by ejecting an alpha particle, the remaining nucleus has only 93 protons. This is a new element called neptunium-237. The decay equation looks like this. Neptunium-237 has 2 less protons, 2 less neutrons, and 4 less nucleons overall. Positively charged alpha particles are affected by magnetic and electric fields, but because they are relatively heavy, they are only weakly bent or deflected. They have low penetrating power and are absorbed in a few centimeters of air or by a sheet of paper. Beta radiation consists of high-energy, negatively charged electrons, which are produced in the nucleus when a neutron changes into a proton and an electron. The electron produced is the beta particle. For example, cobalt-60 is a beta emitter used in medical radiotherapy, equipment sterilization, and irradiating foodstuffs. Here is the decay equation. Cobalt-60, with 27 protons and 33 neutrons, a total of 60 nucleons, emits a beta particle, or electron, and the daughter nucleus is nickel-60, with 28 protons and 1 less neutron. The total number of nucleons remains unchanged. Like alpha particles, beta particles are affected by magnetic and electric fields, but are lighter and more easily deflected. They cause less ionization than alpha particles, being smaller and with a single charge, but they can penetrate further. It takes several centimeters of aluminium to stop beta particles, and they will travel for a few meters in air. Gamma radiation is a form of electromagnetic radiation, like radio waves, heat, and visible light. It is found at the highest frequency end of the electromagnetic spectrum, after X-rays. Gamma rays are produced in the nucleus as part of a rearrangement of energy levels after the emission of an alpha or beta particle. For example, when a uranium-238 nucleus releases an alpha particle and decays to thorium-234, a gamma ray is also produced. Having no charge, gamma rays are unaffected by electric and magnetic fields. They have low ionizing power compared to alpha and beta particles, but being photons or packets of electromagnetic energy are the most highly penetrating of the nuclear radiations. Gamma rays are mostly, but not completely, absorbed by a lead shield several centimeters thick.
Okay, let's look at some equations. In the video they used americium and uranium. They switched it up a little. We're just going to talk about the different types of nuclear decay using one element, and we're going to just choose calcium. Okay, so calcium has a mass number 40 and atomic number 20. When it goes through alpha decay, it loses that helium nucleus. So on the top number here, the 40, we're going to lose a mass number of 4. When we do that, it's going to go to 36. And the atomic number of calcium is 20. We're going to start with 20. It's going to lose an atomic number of 2. So 20 minus 2 is 18. And atomic number 18 is the element argon. And the same thing happens with a beta particle. You can see that 40 minus 0 is still 40. 20 minus a negative 1 is 21. Atomic number 21 is scandium, so it becomes scandium. Okay, calcium and beta decay. Gamma decay. Gamma is mass number and atomic number 0, so it's just energy, so it stays calcium. And here we see neutron decay. And finally, positron decay. Okay, we want to talk about two different types of nuclear reactions, and it's fission and fusion. First, we see here fission. And what happens in a fission reaction is that you have a neutron that's traveling at a high speed, and it collides with a nucleus, a large nucleus of another atom. And when it does that, it provides enough energy that actually can split that nucleus into two different parts. And when that happens, a lot of energy is released, and more neutrons are released traveling at high speeds that hit other nuclei, and it causes a chain reaction. These neutrons keep hitting other nuclei and splitting them and releasing more neutrons. That's fission. Another reaction is fusion, and in fusion you have very small nucleus. It's just a proton and a neutron here, and a proton and 2 neutrons here. And under massive amounts of energy, heat, these two actually fuse together into a nucleus that's got 2 protons and 3 neutrons. Okay, and when that happens, it releases a lot of energy, which then again goes back to fusing 2 smaller ones together into one that's a little larger, and again it produces a chain reaction. 2 examples of these is, of course, we have in the top left corner here our fission reaction. That's what happens in nuclear power plants. And then in the bottom right is an example of fusion reaction, which is what happens in our sun, in the star, which is our sun.